I would like to talk about the definition. For the smaller r, I will define it as the distance between the water and the stick. And for P is the water pressure. And the smaller h is the height of the water. And capital H is the height of the straw. And for A is the cross section. And for R is the caliber. So this is a demonstration video. When we rotate the water pump in the water, we can see that the water will be flow out from the straw. So in this video, we can observe that when we observe the water surface in the straw, it will be a curved water surface, and the water that's flow out from the straw will be droplets. And let's investigate more about the water surface. And the water will flow out from the straw is because of the different water pressure on two sides of the cross section, and it will create a centrifugal force that can flow out the water. So in this equation, the left part will equal to the water pressure, and because the magnitude of the centrifugal force will equal to the centripetal force, so I use the equation of the centripetal force to analyze this. So after some calculation, we can get the relation between the h and r, which the height of the water will be proportional to the square of the radius. So this is my prediction. So the relation between the height and the radius will be a projective function. And if the rotating speed is smaller, the shape will decay faster. So for the experiment, I put the picture of the water surface into image J and get some coordinate location of the dot of the water surface. And then I put the dots into the GeoGebra and draw a fitting line. And this is what I got. We can see that the experimental value will decay faster than the theoretical value. And I think it is because of the friction of the straw. And this is an experimental setup. I use a motor to control the water pump. And here is an adjustable resistor, which can control the resistance of the electric and then control the rotating speed. And here is an infrared sensor, which can emit infrared rays and then to shut on the water pump and then calculate the rotation speed. And the rotating speed will be shown as here, which there is a screen. And this is the setup of the water pump. For the initial water amount, I control it as 500 millimeters, and the depth that the pump is in the water is 2.5 centimeters, and the size of the water pump is 8 centimeters. So this is how I did the experiment. I use the motor to control the water pump, and you can see that the water will force out. And for the pre-experiment, how does the size of the water pump affect? So I try the different size of the water pump, which the length of the side is 4 and 6 and 8 centimeters. And because my limitation of the tool, the fastest rotating speed that I can reach is 6 RPS. And under this situation, I think they are most likely to be a horizontal projectile motion. And the only difference between these three is that the spreading distance and the pumping speed. So this will be the two factors that I will mainly focus on. For the first experiment, it's about the spreading range of different rotating speed. And first, I would like to introduce about the theory, Bernoulli's principle. It means that in a static fluid, its kinetic energy plus the potential energy plus the internal energy will be a constant. So I use the Bernoulli's principle to explain the relation between rotating speed and water velocity. Imagine there are two droplets. And one droplet is inside the straw, and one droplet is that is going to leave the straw. And because their height is similar, so we can predict that the velocity will be similar too. And after some calculation, we can know that the velocity will be proportional to the rotating speed. And also, in the demonstration video, we found out that the water that flows out from the straw will be droplets instead of the water flow. So that means we can use the projectile function to analyze this, which we can know that the spreading distance will be proportional to the velocity, will be proportional to the rotating speed. And these are the variables. For the control variables, I control the initial water amount at 500 millimeters, and the depth of pump in the water is 2.5 centimeters, and the size of the pump is 8 centimeters. For independent variables, I change the rotating speed between 4 to 6 RPS. And the dependent variable, I observe the spreading distance and range. And this is my experimental method, and this is what the result will be. You can see that there will be an inner and an outer circle, and I define the radius of the inner circle, smaller r, and the radius of the outer circle, capital R, and I define the spreading range as the smaller r plus the capital R and divided by 2. And I will explain this more in the discussion part. And this is my experimental result. So we try the rotating speed between 4 to 6 RPS, and we get a relation between the rotating speed and the spreading distance, which is a linear relation. So it is our prediction that the spreading distance will be proportional to the velocity and be proportional to the rotating speed. Also, if the rotating speed is smaller than 4 RPS, the water cannot pump out from the shore. So I predict that the threshold of this situation is 4 RPS that can flow the water out. And also, if the rotating speed is too fast, the water also cannot flow out from the shore because that the form of the water will turn into fog. But because of my experiment, I cannot try I cannot do the rotating speed that is faster than RPS, so I didn't get a threshold, but I think that it will have the maximum amount that can flow out the water. And then I draw the closest and the farthest distance into the graph. We can see that if the rotating speed is faster, the spreading range will be larger too. So I will explain this in the discussion too. So for the second experiment is the pumping speed of different rotating speed. And this is the theory. We can know that the flow rates will be proportional to the velocity. And these are the variables. And for the dependent variables, I observe the pumping speed. And this is how I measure the pumping speed. For the initial water amount, I control it at 500 millimeters. And after 10 seconds, I measure the water amount that was left in the beaker. And I define the pumping speed as 500 minus x divided by 10. So this is my experimental result. So we can know that the rotating speed will be proportional to the pumping speed, which that the flow rate will be proportional to the velocity. For the third experiment is about the pumping speed of different sides of the pump. And so this is the theory. And because that if the size of the pump is larger, the upper pump, the radius of the upper pump will be larger too. So that means it will have a bigger centrifugal force. So that I think the flow rate will be proportional to the velocity and be proportional to the radius. And the experimental method is the same as the previous one. So for the variables, for the independent variables, I change to the size of the pump, which the length of the side is 4, 6, and 8 centimeters. And this is the experimental result. And because in this chart, we can know that if the size of the pumping shore is bigger than 8 centimeters, the water cannot flow out. So we can this is in a situation of the rotating speed is 4 RPS. So we can know that in this situation, the threshold that can pump the water out is 8 centimeters. And for conclusion, the water will be flowed out because of the different water pressure on both sides of the cross section. And the surface of the water in the shore is a quadratic function. And the spreading range is positively proportional to the rotating speed. And the pumping speed is positively proportional to the rotating speed. And the pumping speed is positively proportional to the size of the shore. And for the first discussion, why the spreading is a range, not a line. In this picture, it is an ideal water flow. So if the water can against the surface tension, that it will create a range. So there will be a surface tension that the direction that go up and go down. So if the water that can against the surface tension that go up, that the spreading distance will be smaller than the initial spreading distance. And if it can against the surface tension that go down, then the distance will be larger than the original spreading distance. And also, if the rotating speed is faster, the surface tension will be smaller because if the rotating speed is faster, the shape of the droplet will be more ununiform. For the second discussion, why the water spreading is a droplet, not a flow. So this is the motion of the water. So I divided it into 3 stages. For the first stages is the quadratic function surface, which I have mentioned previous. And when this quadratic function reach the side of the water straw, the water will flow out the water will go along the side and then go up. And for the third stages, the water will pump out from the water pump. And because of the water will have different velocity and their attached area is very small. So if the energy difference is too big, the water will be here to drop this. So this is why the water will be dropped in instead of flow. And this is the end of my presentation. Thank you.
So firstly, I would like to ask, will the length of the straw affect the phenomenon?
Yes.
So will it have the boundary condition?
Can you clarify your question?
Will the length of the straw have the boundary condition?
Can you tell about boundary condition? Oh yes. I think it will be like a peak.
Okay, so will the material of the straw affect the pumping rate?
Yes, because it will affect the friction of the wall.
So will the density of the straw affect the pumping rate?
Do you mean the straw or the liquid?
The density of the straw.
I don't think it have a big effect.
Also, will the water temperature affect the pumping rate?
I don't think it will have a big effect too.
So will the immersion depth affect the pumping rate?
Can you explain more about it?
Since you put the straw into the water,
Oh yes, because that the water, initially there will be a surface tension that will create a height of the water that is in the straw, right? So because we have different depth. Yes.
Okay, so since the small vortex may form into the water when the straw is spinning, so will it affect the phenomenon?
Yes.
Will the resistance of the water affect the pumping speed?
Yes.
And how many times do you repeat your experiment?
For each data I repeated it 5 times.
Okay, so when you start pumping, will the water bounce back into the cup or not?
No, I control to let the water pump out from the vacuum.
Okay, so will the water fill the whole of the straw?
Fill the whole.
Fully
no, because the surface is there will be a water wave in the surface, so the water that go into the straw won't be continuous.
Okay, so is the phenomenon on the left and the right side in the straw similar?
Okay, ideally yes.
Honorable jurors and fellow competitors, I'm the opponent from Team Excelsior, and today I'm going to oppose problem 11, pumping stroke. So, the problem statement said that a simple water pump can be made using a straw cut into a triangle shape, and if we cut it at the vertices, when we partially immerse it in the water and rotate it around its vertical edges, the water may flow out through the straw. And we will need to investigate the pumping speed. And I'll mainly focus on how is the water pumped out by the straw and how is the pumping speed affected by different parameters. And for the report's outline, he mentioned pressure differences and the centrifugal force and Bernoulli's principle and also the projectile motion in his theory part. However, the opponent thinks that projectile motion is not fit with this phenomenon. And in his experimental part, he mentioned the size of the pump and the spreading range, which I think is not appropriate with the problem statement, and the rotating speed and also the pumping speed. For strong and weak points, he demonstrated the phenomenon well with the clear observation videos and has a lot of parameters discussed in the report. And he has good explanation of the setup and also the clear graph which show the data they have and compare the experimental data with the theory. And they didn't compare experimental data with theory, and they have the inappropriate analysis method, which are the range of the spray. I think it's not the problem statement wants, and they didn't consider the immersion depth, which may change if they pump the water out but not put extra water into the cup. And the experimental setup could not collect the water well, and also the deviation between the experimental data and the theory are not well explained. For the points to be discussed, we have 4 different parts of the points, and the first part is the parameters. So we will discuss the straws, the parameters about the straws, which are the length of the straws, to see if it will affect the phenomenon or will it have a boundary condition, and discuss the radius of the straw to see how will it affect the phenomenon and also boundary condition, and the geometry of the straw, and also the different shape of the water inlet or outlet of the straw. And also we will discuss the angular velocity to see how they affect the force acting on this phenomenon. And then discuss about the immersion depth, which may affect the water flow. And then in the theory part, we will discuss the force acting on the water to see how the centrifugal force and the gravitational force affect the phenomenon. And then we will discuss the viscosity of the water, so how will it affect the theory and the phenomenon. And then the third part is the experiment, where we will discuss the velocity of the water flowing in and out, and the pumping radius, pumping stability, and the water flow into the straw. And for the data analysis, we will discuss for some boundary conditions, which are the critical lengths, including angles, and to see how, when the critical boundary condition happens, how will the phenomenon shows, and also the critical angular velocity. And for the deviations, we will discuss the perturbation of the water and also the vortex of the water, which may produce by the spinning straw. Thank you.
Okay, response.
So, will the length of the straw have the boundary limit?
Yes. Because
can I use the chalkboard?
because that if we control the rotating speed, that it will have the force, the centrifugal force that can pump up the water will be sent at different heights.
I didn't agree with you because of the centrifugal force supposed to be changed with the rotating radius, which means if the radius you consider is
know.
Is this part, the radius of rotating will be larger than this part.
Yes, I know. So I said that the heights will be different heights. We will have the different centrifugal force.
Yes.
Right? But if the centrifugal force is not big enough to pump the water, if this straw is too long, then the centrifugal force is not big enough to pump the water out. So it will have a limit.
The opponent agree with you because of when the length of the straw increase, the rotating radius will also increase. So
yes,
they
it
will
will have
make
a bigger centrifugal force to pump out the water.
so
Yes.
and it will produce a bigger centrifugal force, right?
Yeah.
Because we increase the radius of the rotation. So the length won't have the boundary limits. Do you agree with me?
Oh, okay.
Okay. So when the straw radius increase, well, the pumping rate will increase. Do you think it's because of the radius of rotation increases or the cross-sectional area increase?
I think it's because of the radius increase. Because the cross section, I always had it as a vertical, so I think it will always be the same.
Okay. So will the amount of water flow into the straw be the same when you change the radius of the straw?
Radius of the straw. I think the main factor that will change the amount of water that will go into the straw is because of the surface of the water. Because if we are rotating the water pump, it will cause a disturbance to the water surface, so that the water that goes into the water pump won't be continuous.
Why they won't be continuous?
Because it is not a flat water surface, I think.
But according to the continuity of liquid,
Yes.
have you ever heard about it?
Yes, I know.
Okay, so if because of the things won't disappear without any reason, so when the water flows into this is V1, so the water may come out with V2, right?
Yeah.
So do you think the water, so since you think the water may not fully fill the pumping straw, so how is the continuity of liquid?
So what I mean is that just like what I have said in the demonstration video, that the water that fall out from the straw will be droplets. Is that
but that's not a.
inside the straw?
Inside the straw.
The water inside the straw is continuous.
Yes.
Oh yes, I agree with you that the water inside the straw will be continuous, but after it's forced out, it will turn into the droplets.
So do you agree with the water will slowly fill the straw?
Oh, I mentioned that the surface, surface will be a curved surface tension. That will be a curved shape. Yes, so it will not fulfill the whole pump.
So what? So if it's not fully fill the straw, so how will the continuity of liquid?
Here we will have a very little water flow, but it will not fulfill the whole water pump.
So do you consider the cross-sectional area of the water filled in the straw?
I consider it as the vertical direction.
What means the vertical direction?
The vertical direction, there will be a water pressure that points to the outer and a water pressure that goes to the inner. Yes, that is what I define as closed section.
However, the opponent disagree with you because this condition won't appropriate to the continuity of liquid, so that's not a real thing that will happen in the earth.
Yes, but inside the straw, the flow will be, the water surface will be like this, right? So it fits the continuity.
So this condition means that water may disappear when it flows up from the bottom to the top of the straw, right?
Right.
Because of the volume from here is like this, but the volume from here is just like this.
Yes.
So how to explain the disappeared volume of water?
If the velocity that can if the pumping speed here and here is different, so that don't mean that the flow rate will be the same.
Why will the pumping speed be different in this part?
Because of I think it's because of the radius. Because you know that we equal to r in squared, so that the radius is different. I think the velocity will be different too.
I think it's omega. But I still disagree with you because that's not appropriate in the Earth. And for the next question is, how will the emergent depth affect the pump strength?
Because this is the pump and this is the depth, right?
Yes.
So when we first immerse the water pump into the water, then because of the certain tension, that the level of the water will be higher than the air. Yeah. So if the depth is different, I don't think that it will have the same.
But do you agree with me that if the immersion depth is more deeper, it will create a higher velocity for the water, so that will affect the pumping rate?
Yes.
Pumping speed.
Yeah.
Okay, since
also the pressure here is different too, because of the different.
right.
Yes.
So it will affect the phenomenon, right?
Yeah. Yes.
So can you explain how the force acts on the water when the straw is spinning?
This is the straw. So it will have the gravity and the normal force, and the friction. And these forces will create the difference of the water pressure. And also of the centrifugal force.
So when will the water pump out by the straw?
When?
For some, if some force is larger than the other force, so what is the larger force that will affect?
I think these forces will create through the water pressure. Right. So that means if because that the centrifugal force is that is what we imagining, right? So I think the centrifugal force will mostly affect.
Okay, so why do you think it's appropriate to use Bernoulli's equation in your theory?
Because ideally I think the water level that is inside the straw will be static.
But since there will be an air drag or viscosity of the water in the extreme, so the mechanical energy won't conserve, right?
Oh, yes.
So why did you still use the Bernoulli's principle and didn't consider about the energy loss?
So do you think there is a better principle that I can see?
I think you should add some consideration of the energy loss in your Bernoulli's principle, since that if it's a laminar or it's a turbulence.
Oh, okay.
According to random numbers. So, how do you make the viscosity in account of this theory? Sorry, since you didn't mention the viscosity. And if you change the shape of the outlet of the straw, will it affect the phenomenon?
I think whether shapes, what kind of shape you use, it will both flow to the water out. But it depends on it will be different than whether it is able, whether it's ability to pump out the water.
So you mean that the outlet, the shape of the outlet will affect the pumping speed?
Yes, so it will, whatever you use will all can pump the water out, but it will cause the difference of the water pressure.
Okay, so do you think what determines whether water will fill the straw or not?
Okay. 看一下。
For the discussion summaries, that we discussed about the length of the straw to see how will it affect the phenomenon, and the reporter said that the length of the straw won't have the boundary condition, and the water flow out of the straw because of the centrifugal force. However, the opponent thinks that there will be a boundary condition. There won't be a boundary condition for the length of the straw because of the centrifugal force. If we increase the rotation radius, the centrifugal force will increase. And this phenomenon didn't perfectly fit with the continuity of the liquid because the water will not fully fill the straw. This is the reporter thinks, but the opponent thinks that it will fully fill. And the energy loss should be considered along with Bernoulli's principle to make sure it's appropriate to this phenomenon. Thank you.
I'm a reviewer from TUME2, and I would like to ask the opponent. You mentioned that there isn't a boundary condition for the length of the straw. Have you ever considered the friction?
I don't think the friction will make the most effect for the phenomenon, since that the centrifugal force is larger than the gravitational.
I agree with you that the friction will affect. But in my experience, I use the same material to make the water pump.
Okay, for the reporter, you said that you use the operator and immerse it in the water, right? And it may be some difference when the water is pumped out and the tips you immerse in the water will change. So, do you guys have any better considerations of how to stabilize the amount of the parts that is immersed in the water?
I think that we can use the bridges pipe. That means that there is a pipe between two containers. So when we change the height of these containers, the level of the water will be different. So that I think we can control the water level by changing the height of this.
Okay, thank you.
I think we could have a pipe that includes some more waters, and we should have a hole that let the extra water flow out of the box, so that will make the level remain the same.
Okay, so how will you define the pumping speed in your research?
I define it as the final amount and the difference of the initial amount and the final amount.
Okay, how about you?
I think we will collect the water pump out of the straw, and we will calculate it with ml per second.
Can I look at the last page? Oh, no, this one. So I want to ask about the relationship between the shooting angle and the previous page, and the relationship between this.
Shooting angle.
Yes.
In the experiment, I control the shooting angle, but I think that if we change the shooting angle, I don't think the range will have a big difference.
So do you think there's a relationship between?
Partially, but not.
How about you?
I think if we change the included angle, so it will make the water pump more out pump from the outer pump for the
Okay.
part
And how can you control the angle?
Because my angle of the water pump is 60 degrees, so that I think the water will go along the side of the water pump.
And do you think there's a better way to control the angle?
I think we could have 3D printer to print the structure of the straw, so that will make the angle remain the same. Thank you.
judges and worthy debaters, this is the reviewer from Team Media, and today I'm going to review the question, problem 11, pumping straw. So this is a problem statement. So a simple water pump can be made using a straw shaped into a triangle, and then when the tip of the straw is immersed in the water will be pumped out. So they need to investigate how the geometry and other relevant parameters will affect the pumping speed. Their focus is on the motion of the water and the spreading coverage of the different angular velocity and the relevant parameters affect the pumping speed. Okay, so the phenomenon is that the water will pump out of the water when the triangle rotates. And then their theory includes that the Bernoulli principle, centrifugal force, and the projectile motions. Their setup includes motor adjustable resistors, water pump, infrared sensor, and beakers, and water pumps. And they include the size of the water pump, rotation speed, pumping speed, and the size of the pump as their parameters. So this is the pros of the reporters. He used a robot to control the pump, which minimized the manual operation errors, and we think that is a better way to conduct the experiment. And they have clear explanations on the relationship between the theory and the experimental value. For the cons, they should add the discussion part in their theory to make it clearer. This is the pros of the opponents. They ask crucial questions that wasn't mentioned. For example, the boundary condition, which we think that is really important, and I will discuss about it later. And they based the report to clarify the model they used, which is the condition of the water in the straw. But, however, the formula there, we think that is wrong. So this is the first discussion. The opponent asked that, do you think that there is a boundary limit of the length of the straw? And when the length increases, there is bigger centrifugal force. And the reporter says that different height will have different centrifugal force. But for us, we think that the energy loss will caused by the gravitational force at the friction, then minus the centrifugal force. So we think that both did not consider about that. And then the opponent asked, why did they use the Bernoulli principle? And they said that the water inside the straw is static. And we think that we can agree with the reporter in this part. And then the opponent asked, do you consider the cross-sectional area? And the reporter said that they only consider the vertical direction. And we think that the area of the cross-sectional area in the straw will largely affect the water pump out of the straw. Then we asked that the operator you use immersed in the water will have different legs. So how can you stabilize the part immersed in the water? And then the reporter said that they can control the water level. So, and the opponent said that they pipe input with water. We think that there's a better way to do this experiment, is that we can ask for an observer to observe for the conductor and see if the water length change. And then we asked that, how will you define the pumping speed? And the reporter said that difference between the initial amounts of the final amounts. And then we asked that, won't the friction be considered? And the report said that will affect by use the same material in the experiment. However, I think that friction is something that needs to be considered. And the opponent said that won't affect the phenomenon. And I think that may be wrong. And then we asked for the shooting angle, and the report said that they control the angle of the same degree, and then the opponent said that they can use a 3D printer for the structure. And I think that is a great way. And this is our presentation. Thank you.
Okay, this is my concluding remark. First, I would like to remark that the temperature will change the surface tension. So the higher the temperature is, the easier can the droplet leave the straw, and the farther the droplet will fly out. Second, the height and radius will influence the centrifugal force. And third, the main factor of the amount of the water is the surface of the water. And fourth, the water won't fill the whole pump because of the surface tension. And just like what I mentioned, it will have a curved surface instead of fulfilling the all pump. And fifth, the water in the pump is continuous, but when going outside, it will turn into droplets. And we can add some error constant to our Bernoulli's equation to consider the energy loss. And Next, we can use bridges pipe to upgrade the experimental setup. And bridges pipe is which a pipe is connected to containers. So when we change the height of one container, the water level of another will also change because of the water pressure. And I don't think that adding the water in the beaker that you are doing the experiment is a good idea, because that it will cause the water wave of the surface tension and then have some disturbance. And next, we think there is a boundary condition if we consider friction and radius of the spinning to the centripetal force. And in our experiment, three sides of the pump is measured accurately, so the angle is fixed. So I think that the shooting angle is, I control the shooting angle. And there is the threshold of the length of the straw that the water can be pumped out. And also the opponent mentioned that they don't think I can use the projectile motion, but I said that when the water pump out from the straw, it will become droplets instead of the flow. So it won't fit the continuous equation. So that is the end. Thank you.
Okay, thank you. Any questions?
If opportunities, anybody wants to ask? If not, I will ask. Okay, I will go first. You all seem to worry about the friction or viscosity, right? Now, Bernoulli's principle, Bernoulli's equation doesn't take into account of that, right? Is that right?
Yes.
Yeah, okay, agree. But if the viscosity is to be taken into account, or you may call it friction, anyway, are you aware that a steady flow will be a straight flow? A straight flow. The difference is that the profile of velocity will change into parabolas, not as plane. You are assuming every cross-section has the same speed across the cross-section. But for straight flow, it should be parabola. You're not aware of that. That should be taken into account. Right?
Yes.
Okay, right. No, the one thing I am not very sure is that, well, it should be an easy test to deduce the relation between pressures, gravitational force, and also the centrifugal force. Because they're in a non-inertial frame, but they're steady states. If you consider all these three forces, and of course, with viscosity. But you don't, you just use the equation for, I think, horizontal direction, because I think you say the pressure is, you consider the vertical direction, and you're looking at the actual, that's called radial direction, or we say horizontal equation. But then when you use the Bernoulli principle, your velocity is along the shore. My understanding correct? If you use the same velocity you derive from the horizontal equation?
This let me ask relevant problem. Okay, about the velocity direction. Okay, so opponent, the reviewer say your equation is not correct about the velocity, right? Can you explain again how this V proportional to omega square? What's the meaning of this velocity?
Oh, I think I lost the m in the equation.
So the square form is not right, you think?
The correct one is the acceleration equals to r omega squared.
So the velocity v equal to omega r is the direction of tangent velocity, right?
Yes.
Okay. However, not only tangent velocity, right? As Professor Tsai says, the direction of water out the straw have two direction. One is tangent direction, like that if we go to omega. Another is outside to the radius direction, right? So how about the radius direction related to omega?
I think that when the water is flowing out, it will only fit the tangential direction because
what's tangential? Along the straw?
No,
horizontal.
along the straw.
Yeah, that's true. Tangential along what?
This is the circle that the hole is in, and I think it will only fit.
Okay, I know. Right?
Because
okay. Then review how about the problem. Only water only leave the straw in the direction of tangent direction, or also have a radius direction.
I think both. The water may be pumped out to the radius directions and also the tangential directions.
So what's the relation between the radius direction with omega? Later. Okay, pass.
I would like to explain with the chalkboard.
Shortly.
Okay. So when we increase the angular velocities, which means the omega, it will produce the larger centrifugal force, and the centrifugal force will have the components from this part. And if this component is larger than the gravitational force component, then it will start to pump out.
Okay. So I know your condition. You have a relatively slow rotation, so the water very close to the straw. Only tangent direction. However, it also have a slow, small radius.
Because the centrifugal force is what we imagine that in reality it doesn't really exist. So that the centrifugal force won't happen in the only happen in the rotating axis, I think.
Okay. Any shared question? Okay. Let's prepare the scoring. Okay, let me show the score. At first, reporter. 7, 6, 8, 6, 7. Then opponent 7, 6, 7, 6, 8. The reviewer 7, 8, 8, 6, 7. Okay, I think the score is quite average. Then, before we end this